Hello everyone. Let's understand what this chapter is really about. So, when we say insolation and heat budget, we're basically answering one question. How much energy comes in from the sun? How much gets used? And how much goes back to space? We are going to decode how Earth receives energy from the sun, how that energy gets distributed, and how the planet maintains temperature balance. Once this flow becomes clear, climate, winds, and circulation models stop feeling disconnected. You'll see the system as one continuous energy exchange process. So, what exactly is insolation? Insolation simply means incoming solar radiation reaching the Earth. Now think geometrically. Near the poles, the same sunlight spreads over a much larger surface area. So the intensity per unit area becomes lower. There's also a number you should remember. The solar constant is about 1.968 calories per square centimeter per minute. Here's something you need to be careful about. Insolation and temperature are not identical. Maximum insolation does not always occur exactly at the equator. Subtropical regions often receive stronger direct radiation because they have fewer clouds compared to the equatorial belt, which has heavy convection and cloud cover. So never assume equator automatically means maximum insolation in a question. Now, why does the sun heat the earth differently from how the earth heats itself? This is where Wien's law helps. Hotter objects emit radiation at shorter wavelengths. The sun is extremely hot, so it emits short-wave, high-energy radiation. The earth is much cooler, so it emits long-wave, low-energy radiation. Lock this one line in your mind. The sun sends short waves. The earth replies with long waves. That single contrast explains the greenhouse effect later. Incoming sunlight doesn't just pass straight through the atmosphere. It interacts. One major process is scattering. Scattering means light is redirected in multiple directions. That's why the sky appears blue. The atmosphere also absorbs some radiation and reflects some. Just remember this distinction clearly. Scattering changes the direction of light, not the source of light. That small clarity prevents conceptual confusion in objective questions. Now let's talk about albedo. Albedo simply means reflectivity, expressed as a percentage. Fresh snow has very high albedo. It reflects most incoming sunlight. Thick clouds also reflect strongly. Dark surfaces like forests or soil have low albedo. They absorb more heat. And this explains something interesting. Polar regions remain cold not just because sunlight is weaker, but because snow reflects a large share of whatever sunlight it receives. Here's something to be aware of. High albedo is about reflection capacity, not about temperature directly. It's the surface property that matters. So how does heat actually move once it is absorbed? There are three main mechanisms. Conduction is transfer through direct contact. It happens near the surface and the air itself does not move much. Advection is horizontal movement of heat by wind. This is what shifts warm or cold air masses across regions. Convection is vertical movement. Warm air rises, cool air sinks. Be careful here. If heat is transferred by horizontal wind movement, that is advection, not convection. Many students mix these two. Now we move to adiabatic processes. Adiabatic change means temperature changes because of pressure changes, not because heat is added or removed from outside. When air rises, pressure decreases. The air expands and cools. That is adiabatic cooling. When air sinks, pressure increases. The air compresses and warms. That is adiabatic warming. This is the physical logic behind cloud formation, rainfall, and dry descending air in subtropical regions. Let's briefly look at twilight. Twilight is classified based on how far the sun is below the horizon. Civil twilight occurs when there is still sufficient light for daily activities. Nautical twilight occurs when the sun is about 6 to 12 degrees below the horizon. Astronomical twilight occurs when it is 12 to 18 degrees below. The important geographical insight is this: twilight duration depends on latitude. Near the equator, twilight is short, roughly half an hour. Near the poles, twilight can stretch into weeks. So duration is primarily a latitude effect, not just a seasonal one. Now let's enter the heat budget. To simplify calculations, imagine 100 units of incoming solar energy. Out of those 100 units, about 35 units are reflected back to space. The remaining 65 units are absorbed by the Earth atmosphere system. Some reflection happens due to clouds, some due to atmospheric scattering, some due to bright surfaces like snow and ice. The absorbed 65 units are what actually run the climate system. You can think of Earth as a gatekeeper. A significant portion is rejected immediately. Only part of it drives temperature and circulation. What happens to those 65 absorbed units? They cannot just accumulate. Otherwise, Earth would keep heating. So roughly 65 units must also leave the system. Some energy leaves directly from the surface as long-wave radiation. Some is absorbed by the atmosphere and then re-radiated to space. Some energy is transferred through convection and turbulence. Some through latent heat released during condensation. The key idea is equilibrium. Energy coming in must equal energy going out over the long term. And remember, the heat budget includes more than radiation. Convection and latent heat are equally important components. Now let's scale this globally. Low latitudes receive more energy than they lose. That creates a surplus. High latitudes lose more energy than they receive. That creates a deficit. The transition zone lies roughly around 40 degrees north and south. So how is this imbalance corrected? Through atmospheric winds and ocean currents. They continuously move heat from surplus zones near the equator to deficit zones near the poles. That redistribution is what keeps global climate stable. Why does all of this matter beyond theory? Because heat budget controls climate patterns, rainfall distribution, vegetation zones, and ultimately, habitability. If outgoing long-wave radiation gets trapped excessively due to greenhouse gases, the balance is disturbed. Global warming is not necessarily about more sunlight coming in. It can also happen because less long-wave radiation escapes. That distinction is conceptually important. Let's close with a compact consolidation. Solar constant, about 1.968 calories per square centimeter per minute. Sun emits short-wave radiation. Earth emits long-wave radiation. High albedo surfaces reflect more and absorb less. Advection is horizontal heat transfer. Long-term equilibrium means energy in equals energy out. And surplus energy exists mainly within about 40 degrees latitude. If you can think through these relationships calmly and logically, the climate engine makes sense as one system. You are exam ready.